set that you'll find is probably tens, maybe 20 colors at best. Everything outside of that, everyone calls something different. Even in the US, so it's quite amazing. What I perceive to be just another color, has a variety of names. I see orange, it's orange, but there's peach and there's whatnot associated with that particular color and different shades of it. And all these, how do we quantify? Right? So there are perceptual mechanisms in order to quantify this, right? And most of the time we do this based on what is known as color matching. So the idea is relatively simple, right? I have basically some particular light source that's going to emit a color. Right? And then I can quantify because I can measure the spectrum. Right? I can describe that light in color in terms of spectrum. On the other hand, I can say, well, I want to generate an additive model. So I will go out and create 3 lights, right, or illuminant sources that I describe as red, green, and blue. The spectral profiles of which are defined. So what I call red, what I call green, or what I call blue is preset. And yeah, ideally I would prefer them to be this nice little ideal brackets, but maybe they're not ideal. It doesn't matter what they are. But it's something that we have standardized and we will call them as red, green, and blue. Now the question is, if I want to describe a particular color, how do I do it? Right? I can try to tweak the percentages of red, green, and blue that I add together in order to reproduce that particular color. And that's exactly what we do in color matching experiments. Right? So you can have a person sitting in front of a screen and you generate a bipartite field. You say, this is my test illumination. The surrounding field is going to be something that's neutral. Now, the primary lights have to be used in order to modulate the amount of energy in order to reproduce that color. Once you do it, you have a sense of what is the amounts that are mixed together for the 3 primaries. So we do that. We do a color matching experiment. I'll say, well, this is on the left is my color. On the right, I have 3 primaries that I want to mix together. Right? So I will change the amounts in which I mix them together and so on and so forth. And I say, okay, that's what I get. Right? So this is the amount of P1, P2, and P3 that I have to add together in order to reproduce the color. Great, I can keep doing this. Okay? And for different colors, I can end up with different things. You may end up also in situations where, of course, not all additive relationships may give you the particular color. So if that happens, then you have to come back to this side and say, well, maybe I have to add a primary over here in order to change this color in order to get the appropriate match. In which case, the addition here is nothing but a subtraction on the other side. Okay. So we can do this. Now, these experiments on humans work reasonably well. Most people will be able to figure out a primary set in order to match the color that they are seeing. Now, for most people, it's always going to be one set. Very few people may end up with 2 sets of primaries in order to generate the same color. Okay? So the reality is that I can generate a particular color not by a unique combination of P1, P2, and P3, but there might be more than one combination of P1 and P2 and P3 that realize the same color. But most people don't end up with that. Okay? So for most people, making this kind of a match makes a lot of sense. It's knowing how much to add to get a particular color. Okay? So these are the basic trichromats. Now, keep in mind this is a purely linear model. Right? We are realizing a color purely as an addition of 3. Right? So if it's a purely linear model, then a lot of other linear properties will apply. Right? So it doesn't matter how I add P1, P2, and P3. Right? It will always, the addition is the result. Right? So the way I add them doesn't matter. Furthermore, if I want to scale things, right, I apply the scale to my equal scale to all my primaries and an equal scale to my light source, right, matching source, then everything should match. So scale variations across all of them should not matter. and then so on and so forth. These are all basic Grassmann laws or linear laws that apply. So the general paradigm that people have used is that, I generate this kind of a matching system. I will identify 3 primary colors. I will find the amounts of each primary E1, E2, and E3 in order to generate a particular match to a spectral signal T. Right? And those amounts that I end up with, E1, E2, and E3, will describe every color for T. Right? So I'm creating a linear relationship. Now the question is, how do we, of course, present this and do this mathematically? Well, of course, we have to design some set of experiments. And people have done that, and based on those set of experiments, we can generate these curves. So I define a specific set of primaries. These are the primaries that I have. These are the specific wavelengths that I use, 645.2 for P1, 525.3 for P2, and so on and so forth. And I end up generating these curves in order to match many different T's. So, great. So how does this translate to something that you want to measure? So the relationship that we actually build based on this is this representation. And so the curve that we generate is nothing but these curves, right? Discrete values in the matrix that I can represent. Like C1 for lambda 1 to Cn for lambda 2. So I have C1, C2, C3, so I have these columns now, where for every particular wavelength, I have a corresponding median function. So which means that when I have a particular spectral signal, this is the spectral signals that we actually generated, off of which these curves are defined. So I can always, given this curve, this is the underlying matching color. Now, amount of each color that we have for that particular perception system is defined as the integral of C1 and the corresponding T values. That's the color that we are sensing. Okay. Now, how do we translate this color to other primary systems or other color systems? So, of course, this particular set of color primaries are not going to be available to us somewhere else. But our job is to maintain the integral to be the same wherever we go. So how do we translate that? It's relatively easy to do because let's say we end up with a new set of primary, we can measure what the primary is. Right? So now we can generate a particular mixing value for each wavelength. So I end up with a new primary, we'll call it P prime. For that particular primary, I want to get a color matching function C prime. So the desired color that I have, I can generate an equation over here, but it's a matching representation. That says that given a signal T, right, if my color matching function is C prime as my primaries are P prime, I can actually go back to using my original primaries, which are defined under this relationship, CT, right? This relationship should remain the same. So the way I ensure that relationship remains the same is basically saying that, well, this is my primary that I'm currently using. So the signal that I'm actually sensing is some C prime of P times the P prime. If I actually multiply that with C, I should go back to my original measurements on the original primaries. Just this integral. So this is what I'm keeping constant, and I'm solving for these. This over here, this entire system, is the color that match to T that is described by the original primaries P, under which we generate the curves. And the inner portion is the perceptual match to T that is based on using some other primaries. So it turns out this is nice in terms of simple matrix translations, multiplication. So what we really need is not, we don't really care what T is, because that's actually some full spectral set of all colors. They are the same on either side, you can actually get rid of them. And what you end up with is essentially the Cp prime, which is nothing but a 3 by 3 matrix comprised of